Hi, welcome to learn the algorithm with me together. Today let's take a look at a 199 binary tree right side view. So what is this problem talking about? We'll be given a root of a binary tree and then imagine ourselves standing on the right side of it and return the values of the nodes you can see ordered from top to bottom. So first of all, we know that the input will be the root of a binary tree, and then what we return is the values of each node, like here, and the order is from top to bottom. So what we need to return is like a list of integer. Great. And then now, what does exactly mean? We take a look at this, the first example. We have a tree here, like 1, 2, 3, 4, and 5. And now we imagine ourselves like standing on the right side of this tree and see the tree. And what we can see is like we have 1, 3, 4, right? So it's really clear to see that like each node we can see is the rightmost node at that level. Like this is the level 1, and this is the level 2, and this is the level 3, and we cannot see the other nodes like at the beginning of this at this level. So which means which means that we need to find all the rightmost nodes at this level and then return it from the top to bottom. So the output will turns out to be like 1, 3, 4. And we can also have another example, something like this. Like if we have only like 1 and 3, then when we are standing on the rightmost, we can only see these two nodes and just return 1 and 3. And if there's nothing there, just return none. And the number of the nodes in the tree is range between 0 to 100. Great. So that's what I all get. And now, how we solve this? Since I talk about like this is about level, and also we care about the orders. So first of all, the binary search, how we search a binary tree is we can use DFS or BFS. And now we will choose BFS because BFS is just the level order traversal. Like we first need to traverse the nodes as breadth as we could. For example, like we will start to traverse the children node of the root node, like 2 and 3 first, and then after we go through all the nodes at this level, then we'll go to the next level to check whether the node 2 have the children, and if it has not, we don't care about it, and if it has, we have another, something like that. And this is the idea how we work on the BFS. And when we're working on BFS, we also need like what kind of data structure can help us keep travel like travels at each levels. And now we can think of it as a queue. So we will have a queue first and then put the root nodes into it. When we put the root nodes into it, we have to know that, hey, so now we are traverse at the level 1, how many nodes you have? And he can just tell you like, yeah, I have only 1 node. So at this side, this is the level 1. yeah, I can know that only have like one node. So we start to work on the nodes at level 1, and then how we work on. So then I can say we are starting looping at the level 1. Probably we can say each level. And when we are like process each node at each level, what we do is first we are get the node from the queue, right? So first we get the node from the queue, it will be pop out. We already got the node. And when we get the node, we check whether this node is if node is, or probably we can say if it's rightmost node. What we do, we will like then add node value into our result, right? So this is what we got. Like if it is the right node, we will add it to the result. If not, or probably not, if not, no matter which node it is, then what we do is we check whether it has left child. If it has, we then put the left child into the queue, and also check if it has right child. Then we also put the right into the queue. So now we can have like it has the right child, it has the left child 2, and also it have the right child 3 for the first node, right? For the root node 1. So now we have 2 and 3 in the queue again, and then we can, like, I'm thinking, should we like count the levels? But now for this problem, we don't care about like how many levels we have, so there's no need to count the level. So that's fine. And then we continue to go through the rest nodes of this queue. So it means that outside this loop, we also like do the looping, like when there's when the queue is not empty, we continue to do this like process, right? And also now we start to traverse to a next level. And before we traverse the next level, we also need to know the size of the next level. Size of the level. Why? So that we know when we need to stop. It means that at the level 2, we only have 2 nodes. For example, like if we are processing the node 2, we then will definitely to add the node 5, something like that. But when we stop, right? That's the questions we have when we stop here. So before we add in a new node into it, we also need to know like what's the size of the level 2, right? So we get the size of the level 2 and then continue to put the node into it. And first of all, as I said before, we first get the node is 2, and then we check whether it is the rightmost node. If not, we can ignore this and then check whether it has the left child, but it doesn't have, so never mind. And we check if it has the right child, and it has 1, we add 5 into it. And then after this, we go to the next node at level 2. The next node is 3. So then we copy out the 3 here, as I said. And wait, let me check. Yeah, look at this level, get a node. So this is like redundant. So we get no from the queue and to check whether it is the right mode nodes. And then for the node 3, so node 3, it also doesn't have like the left node, but it has the right nodes. Also, we add 4 into it. So every time when we are going to the rightmost node, like 3 and 4 is the end of this level. As I said, it is the rightmost nodes. Then we add the node's value into the results. So this is how we solve this problem, I believe. And of course, like we can do some corner check, like if it has node, the root node of this tree. If we doesn't receive the root nodes, we can just return like an empty result, right? Alright, so this is the idea how I solve the problem using BFS. So what is the time complexity? And the time complexity is because we are traverse over a tree, so we have to go through each node of it until we get the rightmost node. So the time complexity will be like O(n), because we go through each node, and n means the number of the nodes. And how about the space? And we're using like a queue to maintain all of this. So the size of the queue should be the space complexity. And when we have the most nodes, it's the worst case. And I'm thinking that when we have the most nodes is probably when we are working on the most width it has. Like for example, if the third level it has like a lot of the nodes, like 6 or 4, that's the space. So probably we can assume that like it will less than O(n), and we can just assume that, of course, the worst case like O(n), but of course it doesn't reach the O(n). So this is how I solve this problem. And now moving to the coding part, we can start coding based on this pseudocode. First of all, we need to have a queue to put this node, 3 nodes into it. And the queue is like this, and we use a linked list to implement it. And then we also need a list of results to help us to like store the results. So we have a list, putting integer and its result, and use an array list to implement it, because the array list is more flexible and we can continue to add like the value into it. We don't need to have a fixed size on it like the integer array, and because this is a list. And after that, we first need to offer the first root node into it, and then we can start a traversal. And while the queue is not empty, then first we need to know the size of this level, right? And then we start to traverse at each level. And for example, like starting from 0 and less than size plus, and we can first check whether this is the right mode nodes. How we check that? So if I is equal to like current size minus 1 is the end of this level, or we can say end of this yeah, the end of this level. And then we can start to put the values into the results like this. Oh, of course, I forget to pull out the nodes. So pull out the tree node, Q, pull, and add this node's value into it. Oh, probably, let me check it is. Yeah, it is val, not value. And after this, we start to check if it has the left child. If the left child is not known, and then we can put the left child into it. And if the right is not known, we can also put the right into it. And I believe that's it. And then we continue to go through the rest of this level, and after this level we are start to work on next level. And after we clean all the nodes in the queue, we just return the result list, because the result list is already has all the RIMO nodes now. And let's run it. Wait, so now the node is null. Alright, so this is the current case I said before. If the root node is null, we are just return the result. So return an empty list. So the first is the empty list should be initialized at first, and then we can have a queue to help us to start a BFS traversal. Great. And now all the test cases pass. Now already complete using the BFS to solve this problem. Now I also want to talk about how we can use the DFS. And also I need to correct something here, is the space complexity of the DFS. We can change to use another letter to represent it. Is like, well, I'm thinking that the space complexity of the BFS is OW, and what is the W means is the maximum width of this tree. Of course, this is what I said before, like if the current level has a lot of nodes, so it means that it wastes the most space for this approach. So the W means the maximum width. And now I'm thinking to use DFS now. So how we work on using the DFS, and now we are also have the same thing, is that this is the tree we have now. I just simply mentioned that before, like how we are using DFS is we can go as deep as we can do at first, like because I want to get the rightmost nodes. So first I will just go from the right side here, like go as further as I could. But how we decided this is just the rightmost nodes I have, right? So every time when I'm start going to there, like I will say this is the first level. We also think about like this is our first level. And then when I go to the next level, then I will increase 1 for it. Like I also have a value like current level, something like that, to help us to count like this level now I'm working on is which level, right? So now I'm going to the level 2, and when I'm going to level 2, I also added 1 if I go to the next level. Now I will go to the level 3. So I will have a current level to help us to remember like which level I'm at. But like how I know I'm going to a new level, because sometimes I'm just like, if I go as deep as I can, and probably I will go back, and then go to the another side. So if I go to another side, like I'm also going from the level 1 to level 2 again. So how I decided like which time is the first time I go to the level 2? So the question would be like, which is the first time I go, let me make it smaller, to the next level, right? So now probably we need another thing to help us to keep track of it, is that like, now if I just go working on the level 1 and then when I move to level 2, it means that, alright, I already know this tree has at least 2 levels, right? So I will need a maximum level to help me keep track of it, to keep track of like how depth is the tree has, right? So even though like when I starting go to the left side, I go to the level 2, but I will say, hey, I already been to level 3. I know you are not going to a new level, just going back to some level I've been with it before, right? So this is what I wanted to do. Like even though I'm working using DFS, I go to it, go as further as I can. So I will use like a current level and a max level help me to remember like whether I'm traverse like at a new level. So basically for the DFS approach, and I will like have this current level, and also I will need a tree node here to help me remember like I'm working on current nodes. For example, working on this node, and then when I go to new level, I'm working at another node. So when we unstop, right? So if I go as far as I could, when I go to a node, it means that, hey, there's no node here, please stop it. So when I stop is when the node is equal to null, we can just, no, it's null, then stop, right? And also like when I'm at current level, I'm not only checking that whether this node is null or not, I'm also checking like if current level is greater than the max level, it means that I'm going to a new level. Then if it is, I put the node value into the result, right? And also I need to update the max level to tell everyone like, hey, at least this tree has level 2s now or level 3 now. And after I'm working on this level, what I do is I continue to go to the right side, like go right first. After I go as further as I could, and then I just revert back, right? Go as further as I could and revert back and try to go to the left side, right? So after I go to the left side, and I also like go back and then try to do another left side and also do right side again. So this is whole idea like how I work on, like I mean using the DFS. So what's the time complexity of the DFS? So the time complexity is also O(n), and means the number of the nodes. And how about the space? For the DFS, because at first we go as further as I could, so the DFS, the idea of using DFS is like I use a stack to store the potential, the current state, and then I go to next stack to work on another state. So how many stacks or the maximum stacks I have, right? The question is like the maximum stack I have. So the maximum stack is decided by like how deep this tree is. So we can also say it's the height of the tree. So h, it means the max height of the tree. And sometimes, like when we are comparing using BFS or DFS, is like probably if the tree is not that deep, we will probably prefer to use the DFS because it means that we are use less space for it, right? So this is the idea how I solve using DFS, and let's move to the coding part. First, we need to have a DFS function to help us. Like we have the tree node, and also we need to have a list of integer to store our result, and also we need to remember the current level. And for the maximum level, we are not using using the parameter to remember it because the parameter cannot help us to remember anything. So we use a private integer, a global variable to help us to remember the maximum level we have, and probably initialize it as 1 at the first time or 0 at the first time. Alright, so now we start using the BFS. So when the node is equal to null, then we can just stop it because nothing here, we should not do anything. And now at this level, what we're going to do is like we check the current level is greater than the max level or not. If it is, it means that we are go through a new level for us for the first time. And then we add the result to it, like add the value into the result, and also update the maximum level. Right, and after this, we start to like go right, to no right, and also continue to put result. But then we need to add one more level when we are starting to traverse to next level. And when we are going to right, we also go to left. That's what we're gonna do. And this is the part of the DFS. And let's go back to the main part of our function. And for our function, we need to like initialize a result list using array list, which is more flexible, and then pass it. Call the DFS function node result, and what we pass for our current level is already 1 because we're starting to traverse at the first level. And after all this, we need to return the results. And also don't forget, like if the root node is null, we need to return our empty result. So let's initialize here result. And probably using DFS, like I believe we don't need to check that because like the DFS also help us to check whether the node is null or not. But yeah, it's okay, we do a double check here. And now run it. We cannot find it. Yeah, of course, we are not pausing the node, we are pausing our root node. Good. So the test case is already passed, and let's submit it. Yeah. So obviously it's faster than the BFS. So this is how I solved the problem using BFS and DFS. And if the tree is not that high, I mean, have fewer levels, and I will more suggest to use the DFS, which is more efficient on the space complexity. And of course, it will also help us on the time as well. So this is how we can learn the BFS and the DFS uh, according to this problem. And if you think this video helped you, please give me a thumbs up, and that would be a great encouragement for me. And thanks for watching it. See you at next video.